Okay, what you're looking at there is the one MOSFET relay driver manual oscillator. And what I'm going to do is use this circuit to demonstrate one of the more common uses of AC versus DC coupling on an oscilloscope. We've got one of the scope probes here hooked up to the MOSFET drain, and the other probe is hooked up to the MOSFET gate, and also the same thing, the same point, is also the MOSFET side of the gate reservoir capacitor, that 33 microfarad tantalum right there. Okay, and I've also just changed the layout of the circuit a little bit to make it a little bit cleaner. But this is the same circuit as we've been looking at developing in the MOSFETs How Do They Work series. Okay, so obviously we're oscillating fairly slowly there, and I've got the switch over in the linear mode, which means this pot is controlling the speed of the oscillations, and also this pot is providing the return path, rather actually it's an active draining path for the MOSFET gate charge. So we have a very consistent behavior of the thing there. But I can control the rate with this pot. And then I can also get the MOSFET over into a linear response range where the pot controls the brightness of the light. Okay. Past a certain point. And then it gets over into where the relay starts clicking. Okay, so if I want to look at the gate charge, you know, the circuit's being driven by 12 volts. The MOSFET is charging when the relay is pulled in, and the MOSFET is charging when the relay is not pulled in, and then when the gate charge reaches a sufficient value, slightly over 4 volts, the relay pulls in and then switches to the discharge path, and the MOSFET turns off gradually, and you can see the light turning off there. So if I want to look at the gate signal and the drain signal, these are happening at very different voltages. The drain is going from the positive rail to the negative rail. The gate is just fluctuating around 4 volts or something, because that's what you need to turn the MOSFET on and turn it off. Alright, so let's take a look at the scope. Here I've got a slow scan rate going on, and I have the baselines indicated. The A channel is the MOSFET drain, and that one we're going to be looking at 10 volts per division. We have a 10x attenuated probe there. The B channel, first we're going to look at it at 5 volts per division, because I'm going to illustrate what's going on here. Alright, so let's turn them on. Okay, so you can see that stay focused. The A channel is going plus or minus about 12 volts, or rather plus 12 volts 0, plus 12 volts 0, that's the drain. The B channel, which is the gate, is riding along there at 4 volts. We're at 5 volts per division, and there's just a little blip when the gate charge exceeds enough to turn on the MOSFET. Okay, so what if we're interested in just that little blip? Well, what can I do? Well, I can increase the magnification of the channel point, but that, okay, now we're at 2 volts per division, so from the baseline we got 2, 4, and now it's going to disappear off the screen if I go any higher, right? If I go to 1 volt per division, it's gone. Now I might be able to bring it back down with the position marker, but then I lose my offset reference and channel reference and all the rest of that, right? So let's not move the position marker. Let's go back down to where we can see the trace, making that little bump there. Can you see that little bump? Bump, bump. There. there. Okay, so let's look at that little, let's go now, let's put the channel on AC coupling. Okay, here we go, ground, AC coupled. Now, let me do this again. Okay, let's go back to the DC coupling, 4 volts per division run along up there. Let me amplify the channel. Now we're at 2 volts per division, and you can see that little blip a little bit better up there, right? Blip, blip. Okay, now I'm going to switch to AC coupling, and you can see what happened. The DC component of the signal was removed. Now we're only looking at the AC portion, or rather the changing portion of the signal, displayed as if it were AC, going up and down across that baseline, right? Now when we amplify the channel, the DC portion is going to be removed. See, watch. Now I'm going to go down here and turn the channel amplifier. Alright, now we're looking at that trace at 0.2 of a volt per division. Alright, now remember, we no longer know where that center line is, but we can see the changes, and we can tell the peak-to-peak amplitudes very easily now, because we're using AC coupling to look at this channel. Alright, so you can see how before we determined that the level around which this thing was fluctuating was about 4 volts, right? So you can see that as that capacitor, as the relay closes, the capacitor charges very quickly, and then it drains out through the resistances of the circuit, and when it gets to a little bit below 4 volts, the relay opens and the cycle repeats itself. And you can see the output voltage here on the drain, okay? So we've used, we've used AC coupling on the oscilloscope to remove what would be a large displayed DC offset that's not important at our amplification level, and we've turned up the amplification of the scope so that we can see what is of interest, that is the time varying portion of the signal, after we've already determined where that large DC offset would be at this high amplification level of the scope. Okay, so that's one use, probably the most important use, of AC coupling versus DC coupling on an oscilloscope. It's to remove large DC offsets without losing your position reference on the oscilloscope. Thank you for watching.